Good morning.
Good morning.
We are Team IQ, Team Innovative Quintessence. My name is Selvin Jones.
Michael Maxon.
Murphia Chowdhury.
Brandon Barr, he's absent due to a final that he had to do this morning, so we'll be talking in his place. And again, our project is a door-mounted tablet solar system, which will be charging with solar panels.
The introduction overview. The focus of our project was derived from the idea to place a functional tablet device on the front of a professor's door to display their schedule and the changes they make throughout their week. The need that arises from this is how do we keep this tablet charged without removing it and causing hazards with wires.
For our objectives for our design review, we'll be going over the behavior of the system, using a UML diagram, showing you our construction of our detailed design from our functional block diagrams. We also will be showing you a detailed cost analysis of materials.
Right here is our level 0 functional block diagram. As you can see, we have the light coming in, which is our input. This is our system, which is our door-mounted tablet solar charging system. And the power that's coming out is going to be the tablet power. The module that we called it is the door-mounted solar charging system. The inputs are just the light, which is going to be our artificial light source that we're going to use from the hallway lights. The voltage that we need to be implemented into our tablet is about 15 volts, 1.8 amps that we're going to use from our solar panel. And the functionality of this diagram is just going to be the charge of door-mounted tablet via solar panels connected and mounted together for the amount of power that we need for our tablet.
This is our level 1 functional block diagram. Again, you can see lights coming in on a more detailed level. You see it goes into the solar panel system. And we call it a solar panel system because it's not just going to be one solar panel. It's actually going to be multiple solar panels. They're wired together in series or parallel. From our solar panel sensor, we're going to output a 15 volt DC. And this is going into a battery power sensing unit. This unit is used to sense when the tablet is fully charged, therefore diverting the power of the solar panel that's coming out of the solar panel system to the charge storage unit, which will build up the charge and then release its charge once the battery power sensor unit senses that the power in the tablet is below 65%. Again, our modules have a solar panel system receiving an artificial light source, voltage panel, 15 volt DC coming out. This is used to convert the incoming light to desired voltage and power range. Material will be single layered due to the simple design and lower cost than multi-layered cells. It will be the polycrystalline silicone material is less expensive to make, which is lower cost, and the amount of light it is able to convert will be sufficient for the load. Battery power system unit, it will take the 15 volt DC. And also will output that same voltage and amperage. This is used to control the flow of power to the tablet. Once the tablet is fully charged, it will then again allow the solar panel system to divert its charge to the capacitor for storage. Oh, okay. Well, again, on our charge storage unit, it would input a 15 volt DC, output the same. It's there to collect power from the solar panel, and when it's 100% charged, it will then release it.
Here you see is our level 2 functional block diagram. It's more detailed than our level 1. You can see the lights coming in. For our solar panel system, we're going to use single layer polycrystalline silicone material, which is going to be most efficient for our project due to cost-wise and power efficient-wise. Then, as you can see, it's going to go down into our single layer polycrystalline silicone material 2, which is going to be the other solar panel wired in either series or parallel, which we'll probably choose series due to it giving off more voltage. And as you can see, both of the solar panels give off a 15 volt DC power. Here you can see we name our module to be our single layer polycrystalline silicone material 1, which is going to be the artificial light coming in. One of the solar panels will hold about 7.5 volts. It'll be to convert the light coming in the voltage and power range. The material will be a single layer due to the simple design and lower cost. For our other module, we named it a single layer polycrystalline silicone material 2. It's our other voltage, which will be coming in at about 7.5. And together both of them should equal up to about 15 volts. And this will be as well used to for the incoming light and the voltage. And it'll also be a polycrystalline silicone material too.
Alright. For the description of our behavior system, this is our UML diagram. This is called the use case diagram. We chose this because we thought it was the best way to show our overall behavior of our system. As you can see, a user turns on the charging unit, the solar unit. He turns it off. The switching unit charges the tablet from the solar panel, and then it charges the charging unit from the solar panel, and also charge tablet from the charging unit as well. So basically, the switching unit controls where the charge is going from the solar panel, essentially to the capacitor, or essentially straight to the tablet.
Here's our Gantt chart, which effectively shows our work breakdown schedule. Within the course of the semester, we're going to evaluate our system, which is going to take us about 5 days, which will be done from now until the end of December. Within them, we're going to implement our system requirements in our preliminary design, which will be demonstrated in our demonstration. Electrical layout. We'll also design our electrical and our hardware layout throughout the month. Then as we come back in January, we want to purchase our supplies that we're going to use for our project. Then we're going to we're going to start the construction of our actual project, which will be setting up the switching unit, setting up the charging unit, and also setting up the solar panel system unit, which will be done throughout January and January throughout May. And then, as you can see, we'll start our system integrated testing. We'll start testing our product, our design, and we'll start putting everything together by about April to May.
So the conclusions are the level 1 and the level 2 block 2 diagrams, the UML activity diagrams, which is the behavior of the system, and the Gantt charts, which is the work breakdown structure. And for the demonstration, we will be showing how the different orientations and the components will affect our output of the solar panel, and this will help us determine how to get the optimal power needed to charge the device.
Okay. Before we do our demonstrations, we definitely want to open the presentation up to any questions that you may have for us.
For your output voltage selection, how did you determine that? I think I saw 12 volts, 1 point whatever amps,
Okay.
1.2 amps. How did you all come to that figure?
Well, we definitely look at this. We look at the specs of that specific tablet
Mhm.
that we know that we'll be working.
Okay.
We'll be working on specifically,
Mhm.
and that's the data that we received from the data sheet of that tablet.
Excellent.
So that's how we chose that data.
Good. Very good. Very good.
So in order to get that power from the panels, do you think the lights in the hallways is enough, or you need some other source of light to get that much power out?
I definitely think the lights in the hallway be enough due to the fact that we was actually doing our demonstration on 2 small panels, and we was able to receive maybe up to almost up to 5 volts from that. And also,
you can get, but
yeah.
then currents, is something.
Current, I believe we can do as well. I think we will have to manipulate our system a bit when it comes to using different certain kind of resistors. We also noticed that as we put certain resistors in our circuit with our solar panel, with our solar system, that it'll lower down the voltage, but it'll bring your current up a good bit. And also with our series connection on parallel, you get double the current, even though the voltage stay the same. So as we manipulate our system a little bit more and we observe how our solar system treats the light, we choose how we choose the orientation.
Selecting of the type of the solar panel output is important. You don't want to have a big solar panel around this thing, right?
Right.
If it's small, you're not going to get the maximum power you need. So.
Usually already we have an idea about the solar panel that we're actually going to get, which actually kicks out about 15 volts. It'll actually kick out about maybe 3 amps. So during the construction of our actual design, we're going to run into all those details and go over all those problems.
Also, for battery sensing, how is your system going to do that? I wasn't aware that the tablets.
Well,
When you say battery sensing, can you explain that a little bit more?
The way that we're going to do that is we're going to there's going to be a push button switch, and we're going to use a push button switch, which is going to be on our solar panel, which will be used to control the on and off voltage. And during the system, we're going to wire it so that there will be a level switch. A level switch will be indicated by the tablet, the battery life of the tablet. So when it gets low, it'll cut on during and then we're going to wire that into our circuit of the panels, which contact our storage unit, and it'll notify the capacitors whether to use the power stored in the capacitor if there is any, or whether to pull straight from the solar panel.
Yeah. Piggybacking off of what he said, there's multiple ways that we can sense the whether the battery is full or not. One way, based off what he's saying, also examining the current that's trying to be pushed through the circuit. It's another way to sense.
You want this to be automatically done.
Automatically done.
Manual switch.
It'll be like an automatic. It'll be like an automatic level switch.
Sense the voltage level of the tablet, and then if there's not enough, it's reaching the threshold, then it has to automatically, hook in the battery source.
Yes, sir.
So this is all automatic.
Yes, sir. All automatic. This will prevent from overcharge on the tablet. Also increase the life of the battery, the life of the battery in the tablet, because you don't put too much power on the battery will kill the.
Now, I will make a comment. The lifespan of the battery is insignificant. So if it means that you're, instead of having to sense the battery, while that's a nice feature, if that can't be done, my priority is as long as it's getting powered, I can care less if it actually lets the battery drain a little bit or not. Once again, this tablet's supposed to be, obviously it's not going to be the highest end tablet I can afford. I'm going to put something that just runs just enough to run this application. As long as it keeps a charge, even if it's running full blast the whole time, I know that might not be the best thing for the battery, but even if I wasn't using the battery, remember, my other option is to take the power adapter, run that wire across the doorway, and plug it up that way. So if I had to do that, that's what I would do. Of course, that's very inconvenient. That's the whole point of the project. So you can assume that even if it doesn't sense the battery and take care of the battery is not a priority.
Yeah.
Like that's, if you can, that's nice, but that's not a priority. So if you need to work around that, or if that needs, if that's something that can't be done in the time period for the scope of your project, please don't let that be a priority and hinder you from developing that system.
Definitely. Thank you.
One question.
All right.
Now we'll start our demo.
We are going to start a demo. Raphael, you can hit the lights. Other lights as well. Due to time, we won't be able to show you both ways of the orientation of connecting our solar panel system. So we're just going to show you the parallel way of connecting. In parallel, you get your voltage will stay the same in the circuit, but your current will double. As you see right now, we're receiving around about 1.76 volts on the system.
And about 0.13 milliamps.
Also, yeah, you can see we also doing the same thing with the analog discovery, which is the analog discovery is a simple device, something I can take home and use at home, and I ain't got to carry this around all day. So it makes my life a lot easier. I can measure the voltage on here as well, and also I can measure the frequency wave that's also coming out of the system as well.
Now with the demonstration of our panels, this is just an ideal way of how we're actually going to test our system. We're ideally going to have bigger panels which would be suitable for our system. Due to the positioning of the panels on our door, we're going to manipulate it so that our panels will actually receive enough light. So therefore, it'll intake the right amount of voltage and the right amount of current for our system.
One thing that we also noticed when we were doing our demonstration was that the different components that you put into the system can affect the voltage and current in a large way. For example, if I put a large resistor in this circuit, you will see that the voltage will increase a lot, even though we will sacrifice a good bit of current. You can see our voltage increased by almost double in this circuit, where even though we sacrifice a lot of current. This is something that we won't ideally do, but this is just a way that we can manipulate this circuit to reach the optimal power to achieve our goal in charging this tablet.
So during our test documents, we will actually go through a fair amount of resistors and actually see which one will actually be suitable enough for our system. Therefore, we will receive enough voltage and current, and we won't have to suffer a bit loss of the current or voltage.
Just to